All right, everyone. It's time to start our last presentation of the day. This presentation is called Description and Costs of Potential Dust Control Options for the Great Salt Lake, presented by Kevin Perry with the University of Utah Department of Atmospheric Sciences. So let's give Dr. Perry a big hand, and I can't wait to hear what he has to say.
I just want to thank everybody for sticking around to the end of the day, and hopefully I won't bore you too much. This project is one that I've been working on for most of the last year at the request of the state of Utah, looking at putting together a report on the description and costs of dust control options at Great Salt Lake. And that report is now complete. Initial drafts are complete, and this is kind of the first overview of what's contained in that report, public release to be a little bit later. So this all stems from the Great Salt Lake Basin Integrated Plan, which is a partnership from the Utah Division of Water Resources and the U.S. Bureau of Reclamation. The purpose of that Great Salt Lake Basin Integrated Plan is to ensure an ongoing resilient water supply for Great Salt Lake. The first part of this plan, the work plan, was completed in 2024. And the full plan will be completed in 2026. One of the key components of the work plan was a gap analysis that identified high priority research areas where they still needed additional information in order to get the full integrated plan in effect. And there were several of these high priority research projects, including a stormwater study, opportunities for municipal and industrial water conservation, safe yield estimates from aquifers, minimum functional stream flows, quantification of Great Salt Lake evaporative losses, water requirements for shorebirds, and opportunities for agricultural water optimization, and of course the one that I'm reporting on today, which is options and costs for Great Salt Lake dust control. The report, as I said, the initial draft has been completed. The state agencies are currently reviewing it, and it's slated for public release in January of 2026, but prior to the legislative session. And of course, as we all know, Great Salt Lake has been shrinking extensively over the last 30 years. And the part of this that is most concerning from my perspective is the dust that comes off of the exposed portions of Great Salt Lake. And give you an example of what a dust event looks like from the perspective of someone who's out on the lake bed with the dust. Just take a look and listen to this for about 40 seconds or so. So this was just a very short-lived, relatively small dust event out in the middle of Farmington Bay coming from a thunderstorm outflow this last summer. Concentrations in the air at this time were about 3,000 micrograms per cubic meter. I have a towered site out in Farmington Bay that's measured concentrations more than 50,000 micrograms per cubic meter. And this one only lasted a minute. We've had episodes out there that last for hours. But why do we need to consider dust control at all? Well, there are potential health impacts associated with dust exposure. The EPA regulates PM10 and PM2.5. PM10, about half of those particles will end up in your nose and your throat, and a half in your lungs. For PM2.5, most of those end up in your lungs. They have federal standards that are designed to protect human health, but the children, the elderly, and those with pre-existing conditions will often experience health effects at concentrations that are even below the federal standards. But the scientific literature has established very clear relationships between exposure to particulate matter and certain health outcomes. Those that are associated with lung function included asthma, bronchitis, and of course we have cardiovascular problems associated with exposure to dust as well, including heart attacks, strokes, and premature death. So definitely concerning for long-term exposure for that. The dust also contains carcinogens, which, if we are exposed to that over a long enough period of time, may increase the cancer rate of those living downwind of the lake. From the state's perspective, failing to address the dust issues leads to potential federal intervention and oversight into the state of Utah. We could theoretically have violations of the National Ambient Air Quality Standards, which would trigger a state implementation plan that would have to be completed by the Division of Air Quality. And more importantly, there are no limits on what the state could be required to spend in order to reach attainment as part of the National Ambient Air Quality Standards. Just talk to people in California where they've been trying to mitigate the dust from Owens Lake for the last 20 years, and they've already spent more than $2.5 billion with $150 million of annual maintenance going on at that location to deal with that particular dust site. And of course, if you fail to complete the state implementation plan, or you fail to make progress, then that could lead to a loss of federal highway funds, which would cost the state of Utah billions of dollars. So there's a lot of economics at work here, but there's also the economics associated with the health outcomes associated with people that are being exposed to dust as well. So what's Utah's strategy to address Great Salt Lake dust? So the state is now, I can honestly, happily say, is committed to monitoring dust in northern Utah and beyond. The state is committed to installing a dust monitoring network that will be able to answer super important questions that I've been frustrated that we haven't been able to answer up to this point, which is how frequent are these dust storms and dust events, how severe are they, and which are the most vulnerable communities, what are the concentrations in those communities, and what are the exact health risk assessment associated with exposure for the dust? So that's one prong of the state's response. The second one comes from the Great Salt Lake Strategic Plan, which is different from the Great Salt Lake Basin Integrated Plan. The Great Salt Lake Strategic Plan comes from the Great Salt Lake Commissioner's Office. It was published in 2024, and the stated goal of that, which has been supported by the governor, is to restore the Great Salt Lake to ecological health. And the target elevation for that is a minimum long-term elevation of the lake of 4,198 feet. And as part of that, if by restoring the lake to ecological health, you put water back in the lake, it covers up a lot of the dust hotspots, and you get dust control as a co-benefit to lake restoration. Of course, you have to plan for the best, but you also have to take into consideration that monitoring for the dust may reveal significant health hazards that need to be dealt with immediately, or we may have difficulty getting water levels up in the lake in the time frame that we need to protect human health. And at that point, then we can start looking potentially at dust control measures as a policy mechanism to protect human health. So let's talk a little bit about the Utah Division of Air Quality Dust Monitoring Plan. It's currently in a working state, and it's been told that it will be released publicly very soon, hopefully before the end of the year, but if not, shortly thereafter. I've seen working copies of what they're planning to do, and it involves both filter-based monitors to look at the chemical composition of the particles, to look at the metals that are getting transported to the surrounding communities. It has real-time monitors, and it has new sites near Great Salt Lake, and it has new sites near other Utah dust sources as well, because Great Salt Lake is not the only dust source in Utah. The Division of Air Quality has also hired a full-time dust scientist, and the equipment that they're purchasing as part of this will allow them to have real-time dust alerts specific for communities based upon actual measurements of dust in the environment for the very first time. Very excited about these developments. These were made possible by $150,000 of ongoing money from the Utah legislature. The governor asked for $650,000. The state state delivered 150. And we have to personally thank Tim Davis, the Executive Director of the Division of Environmental Quality, Bryce Bird, the Director of the Division of Air Quality, and Joel Ferry, the Executive Director of the Division of Department of Natural Resources, for shepherding that request through the legislative process. That provided money for the dust scientists, but the DEAQ still needed money for the equipment and the site development. And that money has been provided by the Great Salt Lake Commissioner's Office. I want to personally thank Brian Steed for that. So from my perspective, the dust monitoring network has been fully funded, and the plans are in work and will be released as a working document very soon. So very excited about that. The Great Salt Lake Strategic Plan from the Commissioner's Office has set the benchmark of ecological health at a minimum of 4,198 feet. If you look at the left, the lake near its minimum back in 2022, and the right is about 4,198 feet, which is about what the lake looked like a year or two after I moved to Utah back in the early 2000s. But you'll notice that there's significantly less exposed lake bed in the image on the right. But what does that mean for dust hotspots? Well, let's just look at one part of the lake. Let's look at Farmington Bay. The round circles here are the dust hotspots that are in Farmington Bay, and the water, the blue there, depicts what the water level would be in Farmington Bay if we achieved that restorative lake level of 4,198. And the statistics at the bottom shows that that lake level would cover 45% of the dust hotspots in Farmington Bay. And if you can achieve that, then it will certainly reduce the amount of dust coming off of Farmington Bay. And those dust monitors that we have around Farmington Bay will determine if that's enough to protect human health. If not, then you might want to think about dust control measures on the remaining dust hotspots in that region. The organization of the report basically tries to identify metrics that we could use to determine whether or not dust control measures are warranted, and if we end up going down that route, then it would also identify those metrics that we use to identify how effective those dust control measures are. The report then goes on to summarize all of the potential engineered solutions for dust mitigation. The point of this report is to provide the state with a palette of options. I'm not advocating for one or over the other, but the state needs to be aware of all the options, and of course we'll have to look at the trade-offs associated with costs, feasibility, ecological impacts, and unforeseen things before any of these things would be implemented. We're also calculating the cost of implementing each of these dust control measures on a per square mile basis, and then multiplying by the surface area of dust hotspots that exist out on Great Salt Lake from previous research that I completed. So when it comes to dust hotspots, there are many things that control the amount of dust that's emitted from a specific area on the lake bed. Soil moisture plays a key role. If you can keep the soil moist, it increases cohesion of the particles at the surface, and they're not likely to be lofted. Likewise, if you have a surface crust on the surface that protects the underlying sediment from the wind, that can stop wind erosion. You can have vegetation out on the lake bed that slows the wind speed down, or the roots help stabilize the soil. There are some places on the lake where the particle size is conducive for emission. You have small particles. Some places are sand, and some places you have a lot of salt that you can tap into for that as well. But for the most part, the dust control measures look at trying to increase soil moisture, build a surface crust, and reduce the wind speed right near the surface. So there are basically 12 engineering solution options that are in the palette in this report. 6 of them require water. We have permanent shallow flooding. You have dynamic water management, where you move water around to help reform crust. You have precision surface wetting, which is basically just trying to keep the surface moist. You can bury the sediment under a brine cap. You can do drip irrigation and manage vegetation, or you can even use chemical dust suppressants at times. And then we have a palette of options that don't require water, and these include putting gravel on the surface, tillage, And then the other 4 are basically putting obstacles on the lake bed to cause turbulence and drag and to reduce the wind speeds out on the lake bed itself. And you can do that with either natural systems or solid or porous systems. The data that I used to come up with the cost estimates for these come from 2 sources. One is from the National Academy of Sciences report on Owens Lake in California, probably the most studied area on the planet for dust mitigation. That report came out in 2020, so all of the costs there had to be adjusted for inflation over the last few years. And then when I was needing information that wasn't available in that report, I referred to engineers at the Los Angeles Department of Water and Power, who provided unpublished data for use in this report. So I'm just going to quickly go through the 12 options in the palette, and all of them have the same sort of descriptors here. Gravel works by literally covering up the soil. It works best when you have a geotextile fabric that you put underneath the gravel to prevent the gravel from sinking into the playa. It has a very long expected lifetime. It does require some periodic maintenance of raking it if particles get deposited in it. But as you can tell from the picture, it's not very aesthetically pleasing. It doesn't provide any habitat value. And the cost is fairly high. It's more than $45 million per square mile. And we have 70 square miles of lake bed out there that are actively acting as dust hotspots. Tillage. From my perspective, I thought, oh, the crust is important for protecting the surface from erosion, but tillage destroys the crust. And that's true. But this is not your typical farmer's field where they till it and they make a 1-foot-high mound. This is deep furrows, 4 to 5 feet deep, that are plowed when the soil is moist, and you get large clods that are up on top of these furrows, and they're deep enough that they really act to slow the wind down. This is only effective in clay-like soils. It doesn't work very well in sand. So you would have to do an engineering assessment out on the lake bed to determine what areas something like this might even be possible. The advantage of this, it doesn't provide any habitat or aesthetically, but it is super cheap. It's only $615,000 per square mile. Then we have all of these artificial roughness sorts of things where we put obstructions on the lake bed to reduce the wind speed. Here we have a picture from the Salton Sea where they've put out thousands and thousands of straw bales. And these straw bales act as a barrier to the wind, slow the wind speed down, and act as a sediment trap. And over time, these straw bales will collect sediment. And then this is often paired with managed vegetation and drip irrigation so that you can get the sediment there and then you can put vegetation on top of it and stabilize that soil. It doesn't obviously have much aesthetic value. It provides no habitat value, and the costs are about $11 million per square mile without the managed vegetation part, just the using the straw bales. And you have to be very careful to use straw bales that are certified weed-free, otherwise you can get invasives into the lake system. We can also naturally revegetate the lake bed in certain areas. There are companies that are providing seeds, and the state has some experience at trying to eradicate Phragmites and then replanting. But this is very risky because it depends upon Mother Nature to provide the right type of conditions for these plants. And you could spend a lot of money and effort to put these plants out there, and then they could be either inundated by water and killed or killed by drought. But it is a relatively inexpensive method, but there's probably only a limited area on the lake bed where you could have a reasonable chance for success of naturally revegetating. That picture there just happens to be an area of Farmington Bay that's naturally revegetating with pickleweed. You can also put out solid elements. These are very similar to the straw bales, except for they're made out of something like plastic or wood or metal. The lifetime of those depends upon what you make it out of. It's really low aesthetic value, no habitat value unless you built something into that. And the costs are between $11 and $33 million per square mile, depending upon what you use. But there is another option for solid engineered, and that's utility scale solar. These panels act much like those other obstacles at slowing the wind speed down, and you could get a return on your investment, theoretically, of the electricity that comes from that. I'm not saying good things or bad things about any of these, but these are options that the state would theoretically have. Most of which aren't legal right now because it will take a legal change in order for engineered solutions to be on the lakebed themselves. You could have other roughness elements. You can put up sand fences. These serve in much the similar way as the straw bales. They slow the wind speed down. They act as a sediment trap. And the costs vary between $18 and $78 million per square mile. But these porous sorts of things could entrap birds, which is one of the downsides of that, among other things. And then you get to the things that actually require water. One of the things that you can do is you can use a water source, and you can use whip lines or sprinklers or bubblers to try and keep the surface moist. But you need access to a water source to do this. You can pull water from the lake to do it, but that it's going to evaporate. And at Owens Lake, at least, these types of things used 2.6 acre feet of water per acre. So there's a water cost associated with doing that. There's also the possibility of tapping into the underground aquifer that is underneath Farmington Bay, for example. If you can get enough flow from that, a lot of research would have to be done to see if that's feasible or not, but there are places for in situ water that you could tap into. Low aesthetic value, moderate habitat. The cost is quite high, $39 million per square mile. You can do permanent shallow flooding. For example, you could break things up into 10 acre or 20 acre or 30 acre plots and level it and then flood it and keep it wet. This is a super high water cost because you're essentially evaporating fresh water instead of evaporating salt water from the other part of the lake, and it's very counterproductive from that. For example, if you were to do this on a very large scale and flood Farmington Bay and turn it into a freshwater impoundment, research that was done by Dave Tarbotten, professor at Utah State University, determined that that would increase the evaporation, have an excess evaporation of 200,000 acre feet of water if you did a freshwater impoundment. And of course, we're struggling to try and get deliveries of new water of 250 to 750,000 acre feet of water right now. So that's a possibility. It's also about $39 million per square mile, unless you do something large scale like Farmington Bay. Dynamic water management basically moves water around in order to reform crusts. So you can imagine a series of berms or weirs or pumps or dikes and sorts of things that move water around, wet an area, saturate it, and then let that water move on to a different area, and then we'll reform that crust. That crust will last for anywhere from a month to a couple of months, so it's not something that permanently resets the crust, but it can be done on a temporary basis. This does provide high aesthetic value, high habitat value, and it still costs about $39 million per square mile. This is something that Utahns should be really good at. Moving water around, evaporating the water, and creating a brine cap so that the sediment is permanently underneath a thick layer of salt. This has been one of the more effective things at Owens Lake. The cost is a little bit less at about $30 million per square mile, but it doesn't provide any habitat, and aesthetic value is pretty low. Just envision the exposed portions of the Great Salt Lake starting to look like the Bonneville Salt Flats. Manage vegetation. This is basically drip irrigation of native plants out on the playa itself. Water requirements are quite high, ranging from 1.5 to 2.6 acre feet of water per acre. It does provide some habitat. It is moderately appealing to the eye, but it's also quite expensive and quite intensive in terms of the infrastructure that must be put out on the lake bed in terms of the pipes and the delivery systems, and it forever changes the nature of the lake bed if you go down that route. And it's about $44 million per square mile. And last of the palette are the chemical dust suppressants, basically spraying material onto the lake bed to temporarily increase the cohesion of the the surface particles. This is used very often in mining environments and gravel roads and that sort of thing. The Great Salt Lake would be a scale unlike any other for this type of application. It requires large vehicles to move about the playa and apply this. It does require water, and it doesn't last very long. The really super expensive ones last a year. Most of them last 2 to 3 months, and then you'd have to reapply all over again. And what type of things can you use for chemical dust suppressants? Well, they fall in 5 categories. You have hygroscopic salts that pull water from the atmosphere and try and keep the surface moist. You have organic non-petroleum binders. You have petroleum-based products, you have synthetic polymers, and you have electrochemical agents, enzymes, and surfactants. When I was doing research on these, I was finding that many of these are actually toxic to aquatic wildlife, so it's something that you would have to take into consideration. Looking at the costs, I've already kind of been through the basic methodology where we take those costs per square mile, multiply by the surface area. That gives you your initial capital cost. But then you have annual maintenance costs that you have to add on. And then all of these sorts of infrastructure projects have a lifetime ranging anywhere from 5 to 50 years. And so depending upon that lifetime, you have additional infrastructure replacement costs coming down in the future that need to be adjusted for inflation as well. So that's what we did. Big picture. Kind of looking at the 50-year costs associated with these on a per square mile basis. The most expensive ones are the precision surface wetting, the managed vegetation, the sand fencing, and the straw bales, basically. Those are all rather expensive. The moderate costs include the chemical dust suppressants, the moving the water around to reform the crust, permanent shallow flooding, the brine cap, and gravel. And then you have the low-cost options, which are solid engineering, the tillage, and the revegetation of the natural plants. So how much area do we have to mitigate? Well, it depends upon what the dust monitoring network tells us about the needs, but the fraction of dust hotspots out on the Great Salt Lake is currently about 70 square miles. 21 square miles of that is in Farmington Bay, and Bear River Bay has about 13 square miles. And that's the estimate, about 9% of the lake bed acting as a dust hotspot. My research showed that if we leave the crust and the surface crust starts to break down over time, that theoretically the maximum could increase up to 24% of the lake bed, which would increase costs commensurately. Big picture here, it's expensive. Everything here is with a B. These are billions of dollars. Just looking at these 12 different options for Farmington Bay, they would range from $500 million up to $9.5 billion just for Farmington Bay. And looking at the cost for each of the different areas of the lake, you can get a total for the entire lake anywhere between $1.5 and $31 billion. But nobody's going to take one of these and apply it to the entire lake bed. Any realistic dust mitigation plan is going to be a mix of these sorts of things. So those costs basically are the end members that bound the costs, and the exact application of a specific dust control measure to a specific area really depends upon the soil texture and the salinity and the existing vegetation and the availability of water and fluctuating lake levels and the importance of habitats and the impacts on invasive species. All these things have to be considered when you are trying to identify which dust control measure you might use in a given area. And that's not part of this project. That's going to be the next phase, would be an engineering assessment of the feasibility of individual types of dust control measures on individual parts of the lake bed. But I do want to do something to be instructive to show you what some of these hypothetical situations might be. So here's an example of a dust control in Farmington Bay where you use dynamic water management to back water up into Farmington Bay, and then that covers up a significant fraction of the dust hotspots. You use gravel on the sandy soil, use tillage on the area with silt and clay, and then use managed vegetation in an area over near where we already have vegetation on the lake. Something like this would cost an initial investment of about $400 million, and the 50-year cost would be about $2.5 billion. Another scenario, very similar. You use the dynamic water management to cover up about half of the dust hotspots in Farmington Bay. You use some precision surface wetting, some tillage, some gravel, and then you use solar panels over on the side where they're unlikely to be inundated with the lake in the future. Don't know if it's a good idea or bad idea, but it's a possibility. The cost of this one would be about $2 billion, and the 50-year cost would be $3.4 billion minus the revenue from the electricity that you generate. And the last one I'm looking at here doesn't use that backing of water up into Farmington Bay. It does do a little bit of dynamic water management along the Jordan River as it's coming in. But this one's using brine cap. So you have to pump water from the south arm into Farmington Bay to create these brine caps. It has some managed vegetation, has some natural vegetation and some tillage. This one is about initial cost of $1 billion, total cost over 50 years, $6.7 billion. Takeaway messages: many engineered solutions exist. All are extremely expensive. We're talking billions of dollars for even the most cost-effective of these. The expanded dust monitoring network from the DAQ is going to play a vital role in determining whether or not we need to use dust control measures, and if so, which areas of the lake should be prioritized. Of course, I always want to state this, that we really have to look at the water and the ecological trade-offs. This is critical because all of these techniques, some of them would be a very bad idea for the ecology of the lake, and some of them would have significant water requirements. The other thing is that many techniques will require pilot-scale feasibility studies to make sure that it actually works and what the cost might be in our specific area. And the last thing I want to leave you with is that engineered interventions fundamentally reshape the lake bed, and it permanently fragments it and reduces opportunities for future navigability. And I think the point that I'm trying to make with this report is that yes, we could do engineering solutions, but I think that if I have to spend $1 billion, I'd much rather spend $1 billion on lake restoration with dust as a co-benefit rather than going down the engineered solution, which will require permanent, ongoing maintenance for generations to come. So, thank you. Questions? Yeah.
Is there a cost for just putting the water back in?
Yes, you have to acquire the water, and that's what the state's working very hard on right now through the Great Salt Lake. I'm not the expert on that, but Mitt Romney, I think, had an interesting perspective on this, more so than the state legislators. Mitt Romney, when he was looking at the issues associated with Great Salt Lake, he says, this is not a $50 million problem. This is not a $500 million problem. He says, this is a $5 billion problem. And so I think, realistically, it's going to take many hundreds of millions, if not billions of dollars to restore the lake itself. So you have an either or here. Do we want to spend that money on dust control measures, or do we want to spend it on trying to save the lake?
Forgive me if you've already answered this, but have you presented this data to lawmakers and council members, and how have they received it?
Yeah, so this was a study which was funded by the Division of Water Resources, and it's only been shared within state government officials right now to get feedback. It hasn't been shared with legislators. That will happen before the legislative session, but I'm hoping that the takeaway message is that dust control is feasible, but extremely expensive, and we probably want to try and spend our dollars elsewhere. Hopefully I haven't scared everybody too much.
Thank you so much for the presentation. I am curious to know, when this study is released, what newsletter do I need to be signed up for to get notified?
Laura, do you know the answer to this one? GreatSaltLakeBasinPlanning.org? Oh, .gov, yes, okay. GreatSaltLakeBasinPlanning.org. .gov, I did it again. I'm old.
I'm just curious with your study, did you look at some of these engineered solutions, how much dust they would actually stir up with the installation of the solution? Especially with
No, I
tillage.
did not. But you can bet with all construction activities, we all know that when you do construction activities, you generate a lot of fugitive dust. And a lot of these would actually require breaking up the crust, building roads out on the lake bed. It would generate dust. But to get the dust into the surrounding communities, you have to do this, in an environment with really strong winds. And I don't know what the implications would be for actually doing that. So it's an interesting thought, though. Okay.